Okay, so any questions before I get going? Yeah.
So on problem number 2, we thought we more or less had some sort of solution, but it turns out you're giving us a different condition such that whenever there's an empty list, you put out 1 and the rest are 0, or if there's 1 0, you put 2 0.
Okay, here's what I said, because people were asking what happens at the end, and I couldn't come up with an easy way of a coherent way of describing it. So then I said, well, what do we have? We have these zeros, and the problem said the zeros are the separators between the lists. So you have, if you have n zeros, that means you have n separators. And by simple fence post principle, that means we must have n plus 1 lists.
So what happens when there's just 1 0 in the beginning?
All right, so if you have 1 0, how many lists do you have?
2. Then that's followed by a number.
It doesn't matter what it's followed by.
Okay.
That's the beauty of setting it up this way, that it's consistent. That if you have n zeros, you have n plus 1 lists. And so you multiply whatever is in here. You multiply whatever is in here. And then you're done.
On one of your examples, there was a 0 in the middle, and we just jumped over that 0, but we never output.
The zeros are the separators. The zeros are never parts of the list.
But that was when there was 2 zeros.
Right.
So when there's 1 0, it's just a separator.
So in a situation like this, let's say it's 1, 2, 3, 0, 4, 5, 6. Right? This one, is this the case you mean? Oh, yeah.
Yeah, case like that.
Okay. In this case, the output is 6 and 120.
And what is the next thing?
0. But we have reached the end of the iteration.
But that would mean that we have reached an empty list.
No. If you had no, 0 means there's nothing else anymore. That means we're done.
So then why would an empty list be equal to 1?
Oh, okay. So how many zeros do we have?
0. So 1.
How many sequences do we have?
No sequence. 1.
When we have n zeros, we have n plus 1 lists.
So in this case,
So when we have no zeros, how many lists do we have?
no zero. 1 list.
And so that one list would produce a 1. And then we're done, so we get 0.
So right now the problem is we are putting everything this product in a loop, and our first statement is if the list is empty, return a 0. And we have to put it in such a way that if you
But
are
I have an answer to that. Don't do it like that. The end of this, I mean, first of all, if it works in 90% of the cases, I mean, you're going to lose a point or two. Because the importance of this question is, can you do the continuation stuff? And so, if it's inconvenient and you have other things going on in your life, I mean, hand me in the thing that works in the generic case, and I might have a test case or two with this. That was not my particular interest. It's just that people ask me, what is the behavior? And I felt if I looked at my solution and just codified what my solution happens to do, because I'm going to have to redo my solution as well, and did whatever was easy, then that would not be fair, because other people might have had some different way of getting at it. So I said, abstractly speaking, what should be happening, and this abstractly is completely coherent. You have n zeros, that means you have n plus 1 lists, they may or may not be empty.
So I'm thinking the solution to this is very similar to the tree iterator.
It is
Except
indeed.
you just do a bunch of logic to check the condition that you're providing. That's the way that we're more or less approaching it. So
Yeah.
that's why it's kind of confusing when your sample solution has one set of examples that we match exactly, and you throw some curveballs saying, well, when there's a 0, you have to have n plus 1.
You guys just asked what is the behavior.
Right. So
Well,
that's
then-
no additional.
Well, I have to give some answer.
Yeah.
Now that I think of it, the Vietnamese students were smart enough not to ask. They knew there was just a can of worms. And I'm sure my solution, I'm going to have to go back and rework it too. That's icing on the cake. Get the thing to work, and then if you have extra time, then get it to work just like this. And if not, you might lose a point. You'll live. It's the least of your worry. Okay, other questions? So, to reiterate, if you get it to work with, like for the boring examples where everything is, where there's not a zero at the end or at the beginning, you're going to get the vast bulk of the score. So make sure that that stuff works. And then if you have extra time and you're enthusiasts for homework 3 problem 2, then go and finish it up. Other questions?
Did you cover the catch today?
Yes.
I think that's why we're not asking.
Yes. So I thought there were several people who, for whatever reason, said came to me and said they were fuzzy on how exception handling works in a kind of a standard language, such as C++ or Java. And so in C++ and Java, it works essentially the same way. The Java people pretty much imitated what they found in C++, with a few minor things around the edges that I may or may not get to. So to throw an exception, you have you use the throw statement, and it works a little different than in the homework. Here, one throws this exception object, and that's the signal as to what you want to do. What do we do in the homework?
We actually have a catch in our text, and then we call a function.
Now, what does throw do?
Throws a tag symbol.
It throws the symbol along with the argument.
So it throws two things.
Yes.
I see. So it throws the symbol and an argument. And so here it's the exception is kind of the analog of the symbol. You have an exception such as illegal argument exception, file not found exception, array index out of bound exception, null pointer exception. So that's kind of the same thing as the symbol, except in an object-oriented language. Then you have an easy way of categorizing them. So you have a superclass exception, and you have subclasses for these various things. And we don't have that kind of luxury in our little setup. We could have built it up, but it would have added accidental complexity. So when you say throw, then the current method terminates immediately, or as it so charmingly says in the language spec, it terminates abruptly. You do not return to your caller. You do not collect $200, but instead you go in search of an exception handler. So that means when one looks at the call stack, so if I have a function f that calls g, that calls h, then I have on the call stack the locals of f, a return address, the locals of g, and then the locals of h. And the normal way that a function would unwind is it would fish out the return address, lose its locals, fish out the return address, and then it would return into G at the point that this return address points. So that's kind of the normal way that a stack is unwound. But that's not what we're going to be doing here. Instead, now let's say f contained a try block. So the syntax in both Java and C++ is that you have try, some amount of work goes on in the try block, and then you have a catch. And now this would give the exception type here, so maybe IO exception. And you may have more than one catch clause, which we don't have in the homework. So I'm not going to belabor it too much, because you could always simulate that by having just another try and another catch around it. So, and it's also possible, of course, that G contains a try block. Let me make it in red to contrast it. We call H, and let's say there we catch an index out of bounds exception. And now over here, let's say inside H, we're going to throw a new null pointer exception. So then there is a parallel data structure, which may be nested, intermingled with the stack, or it may be completely a parallel data structure that has all of the current try catches. So it has the first one, and it has the red one here. And so at the point of throw, then we need to find our way to the matching catch block. So this one was a catch, IIOBE. This one here was a catch. So when a null pointer exception is thrown, we unwind the stack by just popping off everything that's on the stack. We're looking for the try blocks at the same level. Now we see, does it match? And it doesn't, because we had a null pointer exception. And we keep on going and look at the next try block and see if that one matches. And as soon as we find a matching one, then the hunt for the handler stops, and execution resumes in the body of the catch. What if we don't find a matching catch?
Just output the symbol.
Well, in Java. Well, we don't have a finally. What if you, this would never have happened to you, so you probably don't really know, but what would happen if an exception is thrown in a Java program and there is no matching catch block?
It terminates and shows you a stack.
Yes, so it terminates, and so the default behavior is in fact that you get this stack trace just before that. So in fact, anytime that an exception is thrown at the outermost boundary of a thread, then this thread is terminated, and you get the stack trace. So now let's take a situation where we have a match. Say this one was not a null pointer exception, but an IO exception. Then, as it's important that you realize that this one here is not attempted because it's not matching, and it has to climb higher to find this one.
So if it doesn't match, then it has to pop off.
I would think so, yeah. Now, I had a few people in my office who said that they had a solution to this homework that involved a single global variable that held a single continuation. And I didn't see how that was going to work, because when you, in the throw, it's not known at compile time what kind of thing this throws. And so you could have any number of catches that are pending. And so you would really not have a good idea which one of them is actually going to be the one that's the receiver, which one of them gains control. So you're going to have to collect them all. So in the homework, you're going to have to build some kind of a data structure that contains some runtime information about all of the try blocks that you're building up, except I called them just catches. I don't know why. I could have called them tries. So let me actually explain this somewhere where I have some space. So in Java or in C++, it's try, some action, catch, and then an exception type. And then some handler. And in the homework, how do we do it? It's catch. What does catch take?
Expression.
Is the first expression the action or the handler?
It's action.
So the first one is the action.
And then tag, which is a symbol, type.
And so then it's the, kind of the type, right?
And then
So that's the syntax in the homework. But it really is the same thing. It's just that the syntax in a more traditional programming language, you kind of have these two keywords that really belong together, whereas in, you know what I could have done? I should have called this try catch. That would have been nicer, right? Now I have to find it. Just that was my intention. That it's the try and the catch together. And so it has these three components: the action, the type, and the handler. And I'm just trying to model the exact same thing. So maybe that might make this a little clearer. If you like, I could change the assignment to call it try catch if you find that clearer. If so, someone put a petition on Piazza. I will read it. Yeah.
so you said, let's say I have two catch and throw conditions.
Yes.
So first I encounter a catch and set a continuation. Basically that goes into the data structure.
Right. So let's do this a little bit more slowly. So there has to be some way of getting to. So we're having these things nested. We have a try and catch, and then we have another,
Correct. So
and another. And now as one unwinds them, you have to have some way of jumping here, jumping here, jumping here. And so that is clearly done with a continuation. So somewhere one must, yes.
Talking in respect of the example, the question here,
Yes.
we have. So every catch will have a matching throw, or to say every throw will have a matching catch. Right?
You don't know that.
Without a catch,
I mean,
if an exception is thrown,
yes.
if there is no corresponding catch for it, then there will be no corresponding continuation in the
That's
data
correct.
structure.
In which
So-
case you're supposed to return to the top level.
Correct, which could be the terminating the program also.
Right.
Correct. So my question is, you said whenever whenever I reach a throw, I traverse through this data structure, and if the tag doesn't match, basically I pop it out.
Okay, so just to make sure that everyone understands this, in Java, where you have this nested structure of try-catch blocks, there must be some indication in the Java runtime data structure of what exceptions a particular block might actually catch.
Along with the
So this might be that I can catch this kind of exception, and this can catch this exception, and whatever, just say any exception. And so you will have to imitate that, and so you need to, in your data structure, where you have a stack of these things, you need to have each of them has to have a particular type that it can handle. I guess, I mean, the other way that you could deal with it is you could simply have the continuation that jumps to a point where you make the decision. That's another option. I don't know if it's any better. But it seems like the easiest thing to do seems to be to put this on the data structure. And the more I think about that, probably is the easier way. So then you would have to pop the thing up until you find the matching one. And then you take the continuation that you also stored with it, you call the continuation, and that of course has to get you back where?
To the handler.
So it has to get you to the handler. And so the question then is, how do you engineer that?
So you call the continuation with the handler, and you pass the argument also which you have in the
Yeah, so there's a, I could not easily figure out how to set it up so that it would get to the handler, right? Because how would I do that?
I think what we decided is...
I know that. I'm just trying to get everyone else to understand this problem. So the normal advice for how to do call CC is as follows. You say, you figure out to which point in the execution do you want to return to, and at that point you put a call CC. Where do I want to return to? Yeah, I don't want to go to the action, right? So I want to return to this point. Right? So that probably means that I'll have to take a call CC, maybe it goes inside here, maybe it goes around this thing. Seems to be nothing wrong with putting it around this thing. So here I would have some code where I stash away the continuation. Then I would execute the action. Oh, I guess I also stash the continuation and the type. It's a macro, so I can reorder these things in the macro. Then I would execute the action. And now if something blows up, then that's how call CC works. Whenever you invoke the continuation, you get to this point. And now here was my challenge. Now I'm at this point here. How do I know whether I got to this point because I simply uneventfully traversed the normal path without an exception, or whether I got to it by throwing an exception? Yes, I could do that, and that would actually be a perfectly good idea. You could, at the very last statement here, set a flag. So you could set a flag to false. As the very last statement here, you can set it to true. And then when you come out, then you can check the flag and say, if the flag is false, then the setting it to true never happened, and then I better call that handler. That would certainly work. And what I ended up doing instead is I said, this is too much trouble, and I just put the handler also into this data structure. So in my data structure, I put the type, the continuation, and the handler, because that way I had the handler with me, and it was easy. So you can think of it either way. I think the flag is more intuitive. And now remember, this is a macro, so what you want to do is the same thing as with any old macro. You want to write it down in longhand and figure out what effect do you actually want to achieve. If you want to set a flag, you have to allocate the variable with, I guess, a letrec or let. You have to first initialize with 0, then you have to do a set exclamation mark here, and you actually want to write all of that down before you do the macro that produces all of that. In the other situation, you're going to, in here, you have to build up some tuple or some list. You have to prepend that list to some global list that gives you your runtime stack. Yeah?
So in our previous example, we had H, G, and H, right? H was throwing some error.
Yes?
Suppose H matches that null pointer exception.
Yes?
Then it will be handled there.
Yes.
But now G's catch is actually index out of bound thing. But it will be popped off. So then.
So what you're saying is that even when you return out of this in the normal way, you still have to clean up the runtime data structure. And that is true. You have to.
Yes, but the other case is also, let's say I've reached the null pointer exception first, and to traverse that, if I'm popping out the other exceptions, other continuations, then later if I come across the index out of bounds exception, how will I handle that?
No, that's sorry, what?
So what our idea was, pop it out only
No,
when it
let's
matters.
first of all understand a situation where this would happen.
Yeah.
So you have a try catch for what? For a null pointer?
Yes. Yeah. Yes.
And inside that, you call